Help everyone explore new worlds and ideas. Support your local home for strange and educational content. Nuclear reactors. Don't you just love them? I mean, the blue glow, which by the way is real, and the fuel rods and the radiation and all the safety that goes on, the genius of the engineers and the physicists behind them, and how they could supply a perfect energy. They could supply us with a perfect world of energy if we use them right. I love nuclear reactors. I hope you do too, because today I'm going to be talking all about nuclear reactors. Where they come from, what they are, what they do. But in order to understand a nuclear reactor, you need to understand what they do, splitting atoms. And so, we must understand the atom. Atoms, they're everywhere. Everything is made of them. You know this. I don't need to explain it to you. But what I might need to explain to you is what they're made of and how they work. You see, you've probably seen a diagram of an atom that looks something like this. Now forget that because that's a lie. They look like this. Now forget that too because reality is scary and you don't know quantum mechanics, so let's go back to this. You see those little ball things flying around in orbits? Those are the electrons. They give the atom its negative electromagnetic charge. And they're also what make electricity. Fun fact, electricity is just moving electrons. That thing in the middle the electrons are orbiting is called the nucleus, and it's where 99.99% of the atom's mass is. The nucleus is made up of protons and neutrons, and it's incredibly small. In fact, if an atom were the size of a football field, the nucleus would be a penny sitting in the center of the 50-yard line. The protons are the positively charged particles that balance out the electrons' negatively charged particles. But, as you well know from playing around with magnets, positive and positive repel. So in order to keep the nucleus from ripping itself into 1,000 tiny pieces, there are neutrons that hold the protons together using the strong nuclear force. The number of protons inside an atom determines what element it is, what kind of atom it is. 1, it's hydrogen, like in the Hindenburg. 2, it's helium, like in a party balloon. 6, it's the carbon that makes everything up. Or maybe the carbon in a pencil. Maybe it's even the carbon in a diamond. Doesn't matter, it's still carbon. 8 is the oxygen in the air. 79, that's gold. But when things get really big, this is where they get interesting. 92 is uranium. It's the biggest naturally occurring nucleus in the world. It's 92 protons and 146 neutrons. It's so big that the neutrons are having trouble holding this massive nucleus together. So the atom finds a clever solution. It shoots out a tiny piece of itself, a piece with 2 protons and 2 neutrons. This is just a helium nucleus. 2 protons, 2 neutrons, it's helium. But since it contains protons, it's changed what it is. It's no longer uranium, it's now thorium, with 90 protons instead. Alpha decay isn't the only way an atom can change its identity too. It can put on a blanket and a stick and a hat and become Fuzzy Wizard. It can also, if there's not enough protons and too many neutrons, turn one of its neutrons into a proton by spitting out a negatively charged electron and a photon, a light particle. This is called beta decay, and the electron is called a beta particle. The photon is called a gamma ray. But the next chapter in the history of radiochemistry and nuclear physics is one that's rather dramatic. And so I would like a rather dramatic friend of mine to take it away. Fuzzy! Take it away! 'Twas a dark and stormy night in a dark and stormy time. 1939, Nazi Germany. Then a young chemist was sitting and doing experiments. And my bunker really was a lab, not a bunker. To say that makes it sound overdramatic. But I was doing experiments in my lab bunker thing when I found an unexpected result. And so I picked up the imaginary phone and called my aunt, who is a physicist living in Sweden. Then I picked up the phone, and it was a call from my young chemist nephew, Otto Hahn, and he said that he had gotten an unexpected result, and he told me the experiment he had done. You see, he had shot a neutron at an atom of uranium, and after he did some chemistry and fiddled with everything, he found he had barium, element 56, which has no business being in uranium. This accent is completely wrong, but I'm going to keep doing it. You see, I did some thinking and some math, and I had found what he had done. Incredible. He had split the atom like a staff that is made out of plastic and has been chewed upon significantly by a Rhodesian ridgeback. You see, when he shot the neutron at the uranium atom, it turned from the form of uranium known as uranium-235 into uranium-236. Uranium-236 is cursed, it is unstable, and so it must split into two smaller atoms, one of which was the barium, which young Otto observed. Now, it was not just barium made, there was other stuff too, and lots of neutrons. Several neutrons flew out of the reaction. And, most importantly, a bunch of energy was produced, about enough to make a grain of sand jump. Which may not sound like a lot, but this is one atom. They are tiny things. I'm a physicist. I should not have to explain this to you. I have an element named after me, for Pete's sake. I come in, a Hungarian physicist walking the street in London, unironically named Leonard Szilard. I heard the news of Meitner and Hahn's discovery, and I thought to myself, they say they release neutrons, and that neutrons are the cause of the atom to split. So, if one atom can split and then make neutrons, which go on to cause another atom to split, which cause another atom to split. Oh my lord! Within 16 steps, a quintillion atoms have split. And as I finished walking across the street, I finished the thought. Then I got on an airplane because I thought the United States government should know about this. And so I talked to the United States government. They agreed we should know about this. I told them you could build a bomb and the Nazis could build a bomb. They said we could build a bomb and the Nazis could build a bomb. And I said it would be bad if the Nazis had a bomb, but it would be good if we had a bomb. And they agreed. And then they decided to make the Manhattan Project, a secret program to build a nuclear bomb. Much to my dismay, instead of putting it smack dab in the middle of Manhattan, like the name would suggest, they put it in the middle of New Mexico. Because nothing interesting goes on in New Mexico except for snakes and soon-to-be nuclear explosions. Now, that's where I enter the picture. A not so young, not so dashing anymore, but still really awesome man named Enrico Fermi. You see, I had almost discovered how to split an atom. I just didn't figure out what it was. Biggest life regret. I started working on the Manhattan Project. Stay on track, Enrico. And I conducted an experiment to see how many neutrons are actually released when the atom splits. Because if it's just one, then you're going to get and you're not going to get much energy released. But if it's more than one, then the energy will grow exponentially. If it's less than one, well, then your chain reaction, the splitting of a splitting of a splitting, will just die down, and nothing much will happen. It came back that it was about 1.86 neutrons on average. So, now we just had to actually get a chain reaction to happen. And this is where nuclear reactors come in. Finally, the subject of this video. Back to Fermi. I built a nuclear reactor, basically from my head. Here's what it looks like. Here's a diagram. So, you'll notice a few things. It's made out of graphite. You see, when neutrons fly fly after being split from an atom. They fly really fast. And so you need something to slow down the neutrons so that they have a better chance of actually hitting the atom and not just whizzing past it. Graphite is a material that does that rather well. It slows down the neutrons enough that they're actually likely to hit the uranium atoms. And so we built it out of graphite with lumps of uranium in the middle. The astounding thing was, I built this essentially entirely from my brain. There were no blueprints. I built it from my brain, and then it was there. And we built it under the stands at Chicago University's football field. We have control rods. You see, control rods are rods made of a material that absorbs neutrons. So we take out some of those neutrons, so less atoms are split, and you don't get a runaway chain reaction like in a bomb. We had a good buddy of mine standing on top of the stands with an axe and a rope. And you see, he was pulling the rope. This is the rope. He was pulling the rope to lift the control rods out of the reactor so that the reaction could happen. But when I said cut it so that it didn't spiral out of control, he chopped the rope and the control rods fell into the core. He was given the acronym SCRAM for Safety Control Axeman, which is still used to this day. It worked, because of course it did, because it came from the brain of one Enrico something Fermi. Now, we just had to do this again. You see, the element plutonium can be made by slamming another kind of uranium atom, uranium-238, which is much more common than the uranium-235, which can split. If you hit uranium-238 with a neutron, it will beta decay into another element called plutonium. So this will become plutonium-239, and plutonium-239 happens to be great at splitting. And it was much more efficient than extracting the tiny amount of uranium-235 from the uranium ore. So now we have to build a nuclear reactor to make this plutonium. So we built one in the middle of nowhere in Washington State, and we call it Hanford. Hanford's design was slightly different. They used graphite as the moderator again, because it's a good moderator, okay? But this time, because there's a lot of material going on, they needed to cool it. You see, highly radioactive materials produce a lot of heat, and that heat can cause the material inside the core to melt down, and pretty soon you have what would have been Chicago Noble. That's a portmanteau of Chicago and Chernobyl, and those are two things that should not be in the same sentence. So, to prevent Chicago Noble, they used air as a coolant. You see, the air cooled the uranium and kept it from melting. So, in order to get the plutonium, out of the core, out of the irradiated slugs in the core, they take a big stick, this is not a joke, they walk up to the core of the reactor, they place a big stick, and they push the slugs out into an acid bath. And they dissolve in the acid. Great, now we have highly radioactive acid. That's just as fun as it sounds. But now, it turns out, plutonium dissolved in acid. The acid would much rather bond with a different element instead of plutonium. So, the tiny amount of plutonium, about a dime in 10 tons of nuclear waste acid, can be precipitated by adding the element lanthanum. Once you've added your lanthanum, bada bing, bada boom, you've got a tiny, tiny amount of plutonium nitrate, which is scary. And scary. And you should not be messing with plutonium nitrate because it is scary. I'm being told that I have to shut up because it turns out this is already way over the time limit. Whoopsie daisy. So, bye-bye. See you in the next one. We might have a new character, other than Fuzzy Wizard playing everything. So, bye-bye.